Hello, we are the Goofy Gophers, made up of Bethany, Sam, Matt, Zach, and Isaac, and we are presenting our cricket-inspired jumping robot. So the motivation for making this robot is that in general, robots have a hard time getting up large obstacles and large slopes. So we wanted to create a jumping robot that could avoid these obstacles by merely just jumping over them instead of trying to climb them. These types of robots could be used for search and rescue, delivery, or just places in general where there is unideal terrain. So first we started out by getting an animal model. You'll see that there are 6 pairs of legs across the cricket. The largest pair of legs is the hind legs, has more muscle mass and is much longer, and this is where the cricket's very efficient power to weight ratio comes from and why they can jump so high. These legs have 5 segments, as you can see in the photo. The coxa and the trochanter, or the coxa has 3 degrees of freedom itself as it attaches to the body. And then the femur trochanter coxa has 1 joint or degree of freedom. And the tibia and the tarsus and claw have the last degree of freedom, adding up to a total of 5 joints and 5 degrees of freedom. The crickets rotate their legs down and out away from their body extremely rapidly to propel the cricket up and forward. And so coming to our Discovery Decomp, we basically found a paper that does a kinematic video analysis of a cricket, mapping the joints of the leg on the cricket. And they find out that it is accurate to reduce the cricket leg from 5 degrees of freedom and 5 joints down to 2 degrees of freedom and 2 joints. So coming to our analogy check, we know that crickets can jump distances of about 10 to 60 times their own body length. But due to the size and weight differences of our Robogami robot, we are only aiming for about 2 to 3 times the height. So we will see later what the success is. And so we reduced our hind legs to 2 degrees of freedom with 2 joints, and we attached some front legs that we are going to use to manipulate the jump angles and basically emulate the cocking phase that the cricket uses during their jumping cycles.
Our initial design proposal, we wanted a hind leg jumping mechanism inspired by a cricket that will use springs and some sort of actuator so that once the springs are released, the robot will jump, and a body lifting control to mimic the front legs of a cricket so that we can achieve the correct angular and directional preparation that a cricket will do in order to jump. This is going to be regulated by a servo attached to a gyroscopic sensor so that once the robot reaches a desired angle, the servo will cut off and we will remain at the correct angle. Our initial leg mechanism utilized torsional springs at the joint interfaces at the coxotrochanter femur and the femur tibia interface. This is a simplification we found in one of our papers. As you can see, our preliminary design, we coiled the fishing line ourselves and then cut the fishing line in order to test the feasibility of our robot. And we also wanted to see where the fishing line would best be attached to the robot. And so we found in the second clip that the performance was much better if our fishing line was attached lower down on the robot, which allowed us to coil in the legs more. And we used props to simulate the jump angle of our robot while we were doing this testing.
So we decided to implement a mechanism that allowed for our robot to basically adjust the angle of the body before it jumps. So essentially we created a rack and pinion that's servo driven, and then a gyroscope sensor that kind of goes along with that, that tells the servo to stop once a certain angle has been reached. And once the jumping happens and the legs are released, then the mechanism is also designed to just completely track so it doesn't get in the way of any sort of jumping. And here's a video of that mechanism kind of in action off of the robot.
This is our hind leg jumping mechanism. We have our tibia and femur connected by torsional springs, and our femur is connected to the body that holds the electronics by torsional springs. Final chassis modifications in each leg part are printed in PETG for weight and strength considerations. Crossbars are implemented on the long legs to keep them straight while it's coiling, and it prevents off-center jumping. The The springs are pressure fit into the legs and chassis, and the legs are elevated when not actuated. And they also have limiters on the white portion of the legs so they aren't too low and don't allow the body to rotate and absorb the energy that the springs dissipate. This is the coiling mechanism that we made to wind up the coils on the legs. It consists of a DC motor connected to a worm gear, which is then connected to a 62 gear, which catches onto the coiler that wraps the string. And once the string is wound all the way up, it lifts the coiler off of what's holding it to the gear and allows it to release all of the potential energy that is absorbed in the springs, which allows the robot to jump without having to worry about losing energy back into the motor.
So, like I kind of said, we use a gyroscope sensor to determine what the actual angle of the bot is before it starts to jump. But for all of the different mechanisms to kind of start actuating, we decided to make everything Bluetooth controlled. So the angle adjustment is Bluetooth controlled just by choosing when the servo starts to move, and then it automatically stops at a specified angle within the code. For the leg coiling, that's also Bluetooth controlled, and that's kind of done just by switching on and off using a transistor. So just setting power straight through the motor. We're not using any sort of motor drivers for that. And then the leg release mechanism is also servo driven, and you can also choose when that servo actuates using Bluetooth. So again, once the critical angle is reached for the angle adjustment, the servo stops, and then once we decide to hit jump and then trigger that release mechanism, then the servo on the angle mechanism just retracts. And so here's a video of that mechanism just actually on the bot.
Here we can see the robot when it is in actuation. As you can see, there are stress concentrations building at the body riser interface that result in detachment when the body is jumping. The next two attempts, we tried a high contact, low contact interface for elevating our robot. And finally, we decided to just boil our design down to the jumping mechanism on its own at the very end of this video. And you can see a relatively high jumping power here. Unfortunately, we cannot get consistent actuation. So we were unable to perform testing at this time, but we did want to characterize the horizontal and vertical distances the robot could leap at different propped angles. Bush crickets have hind legs that are roughly 120 to 160% of their body length. And as a consequence, they can jump up to 13 to 14 times their body length, typically. There are other species of cricket that do achieve that higher value, like the 60 that we had mentioned before, but typically this is where they fall. So our robot does align with the upper end of the spectrum, and we would have loved to see how many body lengths it would have been able to jump in comparison. From our testing, it appeared to be roughly 2, but we can't confirm that numerically. So some future work that could be done to get this robot test ready is a more efficient mechanism for the fast releasing of the coiled wire that actually tensions the leg mechanism. We would also have liked to implement a mechanism so that we could have it coil to a higher location. That way we could actually utilize the energy stored in both of the springs. So that attachment spring is what interfaces the leg mechanism to the rest of the chassis. So we would have also liked to modify the chassis to allow for a lower interface of the leg, like the spring-loaded legs, for longer contact with the ground while in actuation. So we could have also utilized another Arduino Micro to allow for more pin headers, so we could attach more circuitry onto the main structure of our bot instead of having pieces that are off and connected by wire. To protect some of our electronics as well, roll cage was an idea that we had, just so that if you do get rotation in the air during the jump, you could protect your circuitry and make sure that you don't damage anything during the landing. So one of the biggest things is developing a more advanced riser that will not limit motion. So ideally, this would have high articulation, so you can have a high control over your angle and orientation, but also retract immediately upon the jumping mechanism being engaged. That way it could be out of the way and you don't meet that resistance that we met before. But that wraps this project up. Thank you so much for your time.